All right, so on page 231, just like I said, continuing with the second derivative, but like what we did with the first derivative yesterday. So we're going to look at the relationships between them. So we said at the end of class yesterday, the relationship of the first derivative to the second derivative is the same as the relationship of what? It was the very last thing we had written yesterday. The relationship of the second derivative to the first is the same as what relationship?
The first to the original.
Yeah, the first derivative related to the original f of x. Exactly. So we're going to use that to try to help us fill in this chart. So if the second derivative is equal to 0 or is undefined at some x equals a, what can that tell us about the first derivative? So think about that relationship we just talked about. The second derivative related to the first derivative is the same as how the first derivative is related to the original. So if you have to, you can maybe use your notes from yesterday. But if f double prime of x is equal to 0, what do we know about the first derivative? Dan?
There's a maximum or minimum there.
Yeah, potential, max or min. A potential max or min. Okay. And then yesterday we also said in the last few comments before we had finished our notes that the second derivative would find what? The second derivative finds what? I think it's on the last page of the notes we took yesterday if you look back. Dan?
If there's a concave or a change in the concave.
Yeah, concave up to concave down, or where it changes. And what's that point called at where it changes?
Point of inflection.
Yeah, so the original has a potential point of inflection. Has a potential point of inflection. All right, so now if the second derivative is greater than 0, what does that tell us about the first derivative? So again, think to that relationship from yesterday. What would we know about our first derivative function? If the second derivative is greater than 0.
It's increasing.
It's increasing. So we said the second derivative, and Dan mentioned too, is about concave up, concave down, and inflection points. So if our second derivative is greater than 0, what do you think our original is doing? If we're talking about concave up, concave down, and inflection points, what do you think our original is going to do if it's greater than 0? Second derivative is greater than 0. I think I heard it over here. Yeah, concave up. Concave up, it's going to look like a bowl. All right, now, if the second derivative is less than 0, what do we know about our first derivative? Decreasing. And then what would we know about our original function?
Concave down.
Concave down. We're on page 231. Okay, now our second derivative changes from a positive to a negative. So what do you think that tells us about our first derivative? If something's changing from a positive to a negative, Dan?
Going from a concave up to concave down, but I don't know exactly what the term is.
Well, we're not going... Changes from positive to a negative. So you're thinking we're climbing, 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 and then we're going to fall.
Oh, for the f prime.
So what?
That's a max.
Yeah, so our f prime of x is actually going to have a max. Maximum. And you mentioned we're changing from,
Concave up to concave down.
so when we're changing, we have a what point?
Point of inflection.
So that's actually what the original function is do. We have a point of inflection.
So is that just called a point of inflection?
Yep, where it's
Difference
changing.
Between either or.
The point of inflection is where it is changing. So, for example, I'm just going to draw this here.
Yeah, but there are two types of changes. It can go from a up to
Yeah,
down
it could
or
go
down
from
to up.
negative
But
to
there's
positive.
no like specific.
No.
Okay.
If it's going from concave up to concave down or concave down to concave up, they're both called points of inflection. It's where that change is being made is where that inflection point is. Okay? Now changes from negative to positive. So our first derivative has what? A min. Very good. And our original f of x would have what at that point? Yep, point of inflection. A point of inflection. So this table can be helpful once we start going through some examples for you to look back at and kind of remember what's going on. And also that page from yesterday, I can't remember what page number that was, page 229, that can be helpful too if you're forgetting. You can look back at that chart. Alright, so on the previous page, we found the first derivative of the function of that x plus 2 to the 2/3 plus 1 was the function right here represented by f prime of x. So we found that yesterday and we used that on the example from yesterday. Well, now we're going to find the second derivative and perform a sign analysis to determine intervals of concavity and points of inflection. So like what we did with the first derivative yesterday, we took a derivative, we created a table with our intervals, and we found when it was increasing and decreasing. We're going to do the same thing today with the second derivative, but this is going to tell us where it's concave up and concave down. Alright, so we have f prime of x, and they give it to us. It's 2 over 3 to the cubed root of x plus 2. So that's what they had given us, and we actually found that yesterday. But we need to find the second derivative. Before we go and take the second derivative of this, we can make this look a little easier to use our rules. So how can I maybe rewrite that? I'm going to leave the 2/3 there. How can I rewrite this part? When we go to take the derivative, it will be a little easier.
Right, it is x plus 2 to the 1/3.
X plus 2. Now, if I bring it to the top, though, what should my power be? Negative 1/3. So this is the same thing. Bring it to the top, make it the power negative. Now it looks a little easier to do our derivative. So we're actually taking the derivative of this now. So we have to drop down the power. So negative 1/3 times 2/3, you get negative 2/9 times the inside, and you have to subtract the power of 1. So if I subtract 1, what's my new power? Negative 4 over 3, good. And then I multiply by the derivative of the inside. Well, what's the derivative of the inside? Just 1, so you don't have to write it, it's just 1. Okay. Now yesterday, after we took a derivative, how did we actually find those critical points? What did we do with our derivative? Yeah, we set it equal to 0. So I am going to write this one back as negative 2, and I'm going to put that on the bottom so my power becomes negative now. So x plus 2 to the positive 4/3. If I try to solve this for x and get x on top, I would have to multiply this to the other side. If I multiply this to the other side, all of this times 0 is 0, and that leaves me with 0 equals negative 2. Is that true? No. So we know we can't solve for x like that. But kind of like we had yesterday, what can we determine from looking at this about our x values? Do we run into trouble? Stevie says we do. Anybody agree?
You put a 2 in there and equals 0, it makes the equation
If we put a positive 2?
Or negative 2.
Negative 2, yeah. If we put in a negative 2 right here, that would become 0. 0 on the bottom, well, that's not going to work. That's undefined. So, at x equals negative 2, now let's think. This is a possible what? And you can use your chart to help you. But we're in the second derivative right now, so of the original equation, this is possibly a what? Representing, yeah, the second derivative represents in the original a possible point of inflection. So I'm going to just write PIP for possible inflection point. So if you want to write it out, you can, but PIP, possible inflection point. And kind of like yesterday, we need to create those intervals in the charts. All right. So my first interval, I start at negative infinity, and I go until my critical point. Well, Stevie told us that's negative 2. And then I'm going to go from negative 2 to positive infinity. So I have 2 intervals to deal with. F double prime of x now we don't have to do all of this because they're just asking about concavity, but I'm going to put f prime of x here, and I'm going to put f of x here. F double prime of x. If we pick a value within here, is f double prime of x positive or negative? Well, if you have a calculator, pick a number within that interval, plug it into your derivative, and see what you get. So some number within that interval. Plug it in, see if that value becomes positive or negative. Anybody find an answer?
Negative.
Yeah, you get a negative answer. All right. If we have a negative answer for our second derivative, what does that tell us about the first derivative? If our second derivative is negative, which means it's less than 0, what do we know about the first derivative? Decreasing. Yeah, it's decreasing. If this one's negative, we know the first derivative's decreasing. If the second derivative is negative, what do we know about the original now?
Concave down.
Concave down. So you can write concave down, or if you want to, if you understand what it means, you can just draw something like this, concave down. Now, in this particular example, they're really only asking you to do this line in the chart and the bottom line, but I added in the middle line. It's a little extra practice to help you with how they are related to each other. So let's go on to the next interval. So within this interval, you can pick any number within that interval. Is f double prime of x positive or negative? Anybody find an answer? Is it positive or negative?
Negative.
You get another negative answer. So once again, we know that's negative, so the first derivative has to be decreasing, and f of x has to be concave down. So let's actually figure out what we know now and what this analysis has actually told us. So, f of x is concave down on just one of the intervals or on both? On both of them. So f of x is concave down on negative infinity to negative 2 and negative 2 to infinity. So it's concave down on both because f double prime of x is negative. It's concave down on both because f prime of x is negative. And it's negative on both intervals. Okay. F of x is never concave up because why? Why is it never concave up?
F double prime of x is never positive.
Exactly, because f double prime of x is never positive. Very good. One last thing we can conclude then. So we can conclude that f of x does or does not have an inflection point. It does or does not.
It doesn't because it never changes from one side to the other side. It's positive, negative, negative.
Exactly. So a point of inflection occurs where what changes? Yeah, concavity. Concave up to concave down or concave down to concave up. Do we change concavity? No, it stays concave down, concave down. So f of x does not have a point of inflection because f double prime of x never changes sign. Does not have a point of inflection because it never changes sign. So it never goes from concave up to concave down or down to up. Okay? Getting a little better with the relationships. All right, let's go ahead and turn to the back. So on the back, I'm going to give you a minute or two. Go ahead through these 16. I don't expect you to instantly know what all 16 are, but take a minute, go through, see if any of them come real easy to you, start filling them out, and after about a minute or two, we'll go back through them together and try to fill them all out. So work on these 16. Take a minute or two, see which ones you can figure out, which ones you really don't know. So you should be answering them with like, it's negative, it's positive, maybe it changes a sign, it's a max or a min. Those are the types of answers you should be answering these with. Point of inflection, maybe. Some of them will be easier than others. Remember, the relationship between the first derivative and the original is the same relationship between the second derivative and the first derivative. That may help you with some of these. You have the two charts that we filled out in yesterday's notes and the one in today's notes. About another minute, and then we'll go over some of them together. So get what you can. All right, let's start to go through these then. So we're going to start out with our original function, and we're going to compare that to the derivative. So we know if our original f of x is increasing, what do we know about the derivative? If the original is increasing, what's true about the derivative?
Positive.
Positive. If f of x is decreasing, what do we know about the derivative?
Negative.
Negative. Okay. F of x has a relative max or min. So what does that tell us about the derivative? The original has a max or a min. So what's going to happen with the derivative at that point?
Change the sign.
Yeah, very good. Change the sign. All right, f of x has a point of inflection. What does that tell us about the derivative? The direction is changing. We have a point of inflection. So what does that tell us about the derivative?
Max or min.
Has a max or min. Very good. If the original is concave up, what do we know about the second derivative? Stevie?
Positive.
Positive. Yep, you guys are doing pretty well at this. Concave down then means it must be negative. Alright, so if f of x has a point of inflection, what does that tell us about the second derivative?
Change the sign.
Yep, change the sign. For 8, f prime of x, so the first derivative is increasing. What do we know about the second derivative? Stevie again. Positive. You're on fire, Stevie. The next one, if f prime of x is decreasing, what do we know about the second derivative?
Negative.
There we go, Stevie. Negative. Good job. All right, number 10. The first derivative has a relative max or min. What does that tell us about the second derivative?
Cold wants this one.
All right, Colton.
Change the sign.
Not quite.
Gave you this one.
All right, so let's think about this. F prime of x and f double prime. So that would be the same as relating the original to the first derivative. So if you think an original has a max or min, the derivative has to be what? A max or a min. So yeah, let's say we have a max right here, and you take the derivative at that point. What's the derivative at that point if that's a max? 0. So if you have a relative min or max, you're either going to get equal to 0 or undefined. (11) The first derivative has a point of inflection. What does that tell us about the second derivative? Max or min? (12) The first derivative changes from negative to a positive. What does that tell us about the original? The derivative changes from negative to positive. So what do we know about the original? Minimum. (13) is very similar. The derivative goes from positive to negative. What do we know about the original? Max. Has a maximum. (14) The derivative has a relative max or min. What does that tell us about the original? Steve?
That's the point of inflection.
Yeah, potential point of inflection. It's changing directions. So it's changing direction. So the original has a point of inflection. All right, 15. The second derivative changes from positive to negative. What do we know about the first derivative? Max. Very good. And 16 is very similar. The answer to 16 is min. All right, very good. Any questions on those?
10 and 3.
All right.
Why are those good?
10 and 3. Let's look at them. All right, so for 3, we have f of x has a relative max or min.
Yes,
So the derivative is changing signs. So let's think about that. On 3, let's say we have a maximum. The derivative would be positive here and negative here. So it is changing sign, but down here we have is equal to 0 or undefined. You could interchange these answers. If you think about this, if you take the derivative at that point, is it 0? If you take the derivative right before that point, what is it? Positive. What about right after the point? Negative. So it is changing sign, or it could be equal to 0. So those answers really could be interchangeable. You could have both answers for both of them. Okay? Any other questions? Good question. All right. Down on the bottom then. So the bottom is going to tell you to use the next page. I think we have, the next page will look something like this. It has 15 graphs on it. So you're going to use those 15 graphs in this chart and fill out this chart. Now, what you're going to do, I'm going to give you some time to work on your own. You can work with a partner beside you or whatever. We have some time left. I'm going to help you out a little bit with this, though, to get the ball rolling. So what you need to do is there's, well, 15 graphs. You got to find 5 original, find their derivatives, and then find the second derivative of them. But I'm going to help you out. I will give you the original one so you know which numbers are the originals, and then you can go from there. So number 9 is an original graph. Number 15 is an original graph. 10, 2, and 4. So use that. Those ones are originals. Use everything we've gone through. You can use the charts from yesterday's notes and today's notes. number the rest out. The derivative of number 9 would be what? And then the second derivative of number 9 would be what? So go ahead. If you want to have a partner, you can. I don't care. Use the next 10 minutes or so and work through this.
How do you know? One and negative two.
Yes. Sure.
It'll be helpful to use your critical points, like where is it changing directions, max and mins, use those and what you know about derivatives.
Because if f prime x has a min,
Going through these, it might be helpful if you don't cross out the whole graph, but maybe put check marks on the one that you've already used so you don't use it again. Each graph will be used once.
no, but it has to go straight to the middle.
The 3 sharp points are 12.
11.
What's that choice? No. You go 10, you go 4.
It's the same thing, so this one's Steve.
Why?
Oh, so you're saying it's
If you're having some trouble with these, think about your powers. If you have a quartic function and you take the derivative, the first derivative would then be what? The cubic. And then if you take the derivative of the cubic, you're going to have the squared or the quadratic. If you get to something and you have a quadratic and take the derivative of that, your next derivative would be linear or a line, yes. So use that to your advantage.
x-intercept 1 and 2. X-intercepts are negative 1, 0, and 1. So that's the same thing.
You guys find any of the first derivatives?
Number 4 is about 2 responses. I agree with that. The first one about 12, I agree with that. And then your 11, I go over.
Oh, yeah.
Why is it 7 and not 11? Switch to 11.
Okay, so at this point, the derivative is negative. So right here, this is at 2. So pay attention to your this graph, you would see horizontal
I honestly thought
and ending with 2. Negative, negative, negative. And the negative, and the negative crosses through 0 now.
the first row is closest to the row.
Little hint, one group did find the first derivative of 9 would be number 12, so if you haven't found that, I can help you out a little bit. You guys find any other first derivatives?
12 and 13.
So we got the 12 put up there. 6, I like. 13, I like. Another group found that the first derivative of 15 would be number 6. You-
15 a quarter?
Oh, 11.
Cuban x interception.
You find any other first derivatives?
6.
That's what you know. I got what's number 5?
For number 3, we had 1 should be your derivative. So go ahead, use those for a little while, see if you can find some more.
I agree with those.
If you guys would like to check, the second derivative of the first one should be graph number 3.
I had 7 pre-marked off.
So as you're working here, I'd like to ask some groups for some answers since we're running out of time. What we can do is we can get some answers up here. You can check any answers you may have. And if you have questions with them, when we have next class, you can ask questions. We can go over the graphs when we have more time. Was anybody able to find the second derivative for number 2? Daniel?
For number 2, 7.
Number 2.
What?
I don't think.
Number 2.
Yes,
up
for
there?
number 2,
No,
sorry.
Number 2 up there, not the actual number 2.
Yeah, sorry.
14.
Yes, for problem 2, the second derivative would be 14. So, a better way to ask the question, I guess. The second derivative of graph 10, which is problem number 3 here, does anybody have that answer? Go ahead, Joseph. 11, yeah. Very good. For the fourth problem, what was the first derivative down here? We have 13. And then the derivative of graph 13, so the second derivative would be what? 7. Yeah, good job, Stevie. And we have 2 left.
5 and 8.
So the first derivative has to be graph 5, and the last one has to be graph 8. So again, those are the answers if you want to write those down. If you have any questions, we can go over those next class if you have any questions about them.